When we are doing truss analysis, there are two main methods of analysis that we can use. This video, we're going to focus on method of joints, and a later video will focus on method of sections. So with this method of joints is useful when you want to figure out the forces in all of your members. What we want to do is, if possible, figure out my reaction forces. So to figure out my reaction forces of my entire system, I need to draw the free body diagram of my entire system. So let's draw that. And this is going to have those two external forces on it. So my 3 kilonewton force and my 4 kilonewton force. Now, I have two reaction forces I need to deal with. I need to deal with my reaction force at A, and I need to deal with my reaction force at C. A right here is a pin, so that means I'm going to have a reaction force in this Y direction, and a reaction force in this X direction. C is a little bit more tricky. So C is a roller, so that means I know I have a reaction force that's a normal force to the surface it's on. It's on a 30-degree angle. So this is actually going to be applied at point C right here. But we got to figure out what angle this force is on. So I know that, let's draw this like this. Okay, so I know that this is 30 degrees. If I draw a line straight up, I know that this angle right in here is now going to be 90 degrees. So this means this must be 60 degrees. And I also know that this angle, even though I didn't draw it like too well, is perpendicular. So I know that. That means this angle right in here must be 30 degrees. So if I draw a line down, this must be 30 degrees. And we'll call this my normal force of C. Now, I have my equations of equilibrium. So to determine my reaction forces, I can use the sum of the forces in the X, the sum of the forces in the Y, and the sum of the moments about a point. I'm actually going to start with the sum of the moments about a point, and I'm going to choose point C, which is right here. I'm going to choose this because AX goes through this point, NC goes through this point, and I won't need to deal with any of the components of that reaction force of NC. I'll only need to deal with the components when I'm dealing with the sum of the forces in the X and the Y. So if I sum my moments about C, this is equal to 0. I'm going to have AX goes through that point. And let's say this is my positive rotation. I'm going to have minus AY times this distance, which is 4 meters. Okay, I'm going to have a plus 4 kilonewtons, it rotates head first, times 2 meters, the perpendicular distance. And I'm also going to have this 3 kilonewton force, which is going to be about point C, a minus 3 kilonewtons times its perpendicular distance, which is 1.5. And that's going to be equal to 0. So let me solve for what this is. I'm going to have 4 times 2. That's 8 minus 3 times 1.5. Bring this to the other side of the equation. And divide by a minus 4. I get AY is going to be equal to positive 0.875 kilonewtons. This positive means that this assumption is correct. The reaction force is pointing upwards, which is important when we get to looking at the individual joints. Okay, so now let me look at the forces in the X and the forces in the Y direction. If I look at the X, I have this AX right here and this 3 kilonewtons here. They're pointing in the positive direction. So I have AX plus 3. And then this, the component of X, is going to be minus NC times the sine of 30, right? The sine is the opposite of the 30 degrees. So I get that x component. And this is equal to 0. Okay, I don't have what NC is yet, so I need to go to the sum of the forces in the y. If I go to the sum of the forces in the y, this is equal to 0. What do I have? I have AY, I have minus 4, and I have some component of NC. So I'll have AY minus 4 plus NC times the cosine of 30 is equal to 0. Now I know what AY is. AY is actually 0.875. And I can solve this. I can do 0.875 minus 4. Bring that to the other side of the equation. And divide by the cosine of 30. And I'll get that NC, my normal force NC, is equal to a positive 3.61 kilonewtons. That's great. Now I can plug this NC into this equation. And when I do, I get AX plus 3 minus 3.61 times the sine of 30 is equal to 0. Let's do that. 3 minus 3.61 sine of 30. Multiply it by minus 1. So AX is actually equal to minus, we'll call it 1.2 kilonewtons. This minus sign just means that this AX is in the pointing towards the left. So this is equal to 1.2 kilonewtons to the left. So now we've figured out our reaction forces of this structure. The next thing we want to do is we want to go through all of the different pins that we have. So C, B, A, D. We want to draw a free body diagram of those individual pins. We don't want to do it all at once. We want to take one pin at a time. And we want to learn what, if we learned, for example, that at pin A, that A is pointing the other direction, we want to make use of that information. Now, you typically want to start with the easiest ones to work with. And I think pin A or pin C is going to be the easiest pins to work with. I'm just going to start with pin A. You do have choices on how you go about this problem, but always make it as simple as possible for yourself. Try to pick joints that have the least amount of members. So this has 2 members. This has 2 members. This right here will have 3 members. This right here will have 3 members. The idea between the method of joints, so let's do A. And this right here is joint A. The idea is whenever you have an unknown force, you assume it's in tension. Tension pulls away. So I have this force that goes up like this. This is going to be some force AD. It's unknown, so it pulls away, and I draw it in tension. I don't know what FAB is, so it pulls away, and I draw it in tension. I do know what AY and AX are. AY is pointing upwards, so AY is going up, and it's 0.875 kilonewtons. AX, we learned that it's pointing towards the left, so now we can draw it in like that. So if I draw it towards the left, I know that this is 1.2 kilonewtons. I still need to figure out what that angle theta is. So that angle theta is this angle in my main drawing. So I can figure that out by taking the inverse tangent of this distance, which is 1.5, over this distance, which is 2. So the inverse tangent of 1.5 over 2 is going to equal to 36.9 degrees. So this will be 36.9 degrees. Okay, so I drew the free body diagram of this joint. Now I need to use the sum of the forces in the X and the sum of the forces in the Y to figure out what my unknown forces are. So those are the only two equations I have in method of joints. A joint, we can think of it as sort of a particle. So we have no moment equation. So let's look at this. And I'm actually going to start with the sum of the forces in the Y. My pen is dying, so I'm going to need a new tablet pretty soon. That's why all those weird lines are always happening. But I'll have 0.875 plus FAD times the sine of 36.9 is equal to 0. Now I can solve for what FAD is equal to. What I'm going to have is 0.875, move it to the other side of the equation, divided by the sine of 36.9. And I get FAD is equal to minus 1.46 kilonewtons. This minus sign, so a minus sign means compression. A plus sign means we were correct and it's in tension. So a minus sign means this is equal to 1.46 kilonewtons in compression. Now we don't do anything with that right now. We just note that it's in compression. So now we also need to do the sum of the forces in the X direction, which is equal to 0. Okay, so here I'll have minus 1.2. I'll have plus FAB, which I don't know. And then I'll have plus FAD times the cosine of 36.9 is equal to 0. Okay, well, I do know FAD, it's minus 1.46. It's very important to keep the minus sign when you're plugging it back into the equation because this free body diagram is drawn with it incorporating the minus sign. So this FAD right here will be minus 1.46, and I can solve for what FAB is. Minus 1.46 times the cosine of 36.9. Then minus 1.2. Bring it to the other side of the equation. And I get FAB is equal to positive 2.37 kilonewtons. So that means that this is positive, so that member is in tension. So now we figured out this and we figured out this. What I want to do is I can go to point B. If I look at point B, I want to draw the free body diagram of this point. So at point B, this one's going to be easy because I don't have to deal with any components. I just have to remember to draw in all my forces. So I have this 4 kilonewtons going down. I have, now this is where we use the previous information. This is FAB. FAB is in tension, so we still draw it in tension. If, let's just say, if this was a minus 2.37, and we were drawing this, so we learned that it was in compression, we would actually draw the free body diagram by, it's now a known force, so we draw it in compression. But since it's in tension, we still draw it away, and we can say that this is equal to 2.37 kilonewtons. We don't know FDB, so FDB is pointing upwards. It's in tension. We assume it's in tension. And we don't know what FBC is. Again, we assume it's in tension. So these are the forces I have. Well, this one's pretty easy, right? This, if I sum my forces in the X, what do I get? I get minus 2.37 plus FBC is equal to 0. So I know FBC is equal to 2.37. Let me move this over a little. Kilonewtons. So this would be in tension. If I sum my forces in the y, this is equal to 0. I get F dB minus 4 kilonewtons is equal to 0. So F dB is equal to 4 kilonewtons. It's positive, so it's also in tension. So this one was really easy. Okay, and so let's check off. I know what this one is, and I know what this one is. So all I need to figure out is I need to figure out force of DC. So when I'm trying to figure out the force of DC, I can either use C or I can use D. To me, C is going to be an easier one to figure this out. There's less members that go into it, less chance of mistake. So at point C, what do I know? I know that I have a force that goes like this, and this is going to be my NC force. My NC force is 3.61 kilonewtons, so this is 3.61. I know that I have a force BC. BC is in tension, so it points away. And we know BC is 2.37 kilonewtons. I'm going to put it down here. And then the force I'm looking for is going to be this force right here, which is going to be this force. It's unknown, so we point it in tension, FDC. Okay. So now we just need to sum our forces in the X or the Y direction. I'm going to choose the Y direction because there's less forces in the Y direction. So if I sum my forces in the Y direction, what do I get? I'm going to get 3 point, this angle right here is 30. This angle right in here is this theta angle. So I know I didn't draw it very nicely, but these are two different angles. So we're going to have 3.61. In the Y direction will be the cosine of 30. Then we're going to have plus FDC. In the Y direction is going to be, in this case, the sine of theta, which is 36.9. And that's going to be equal to 0. And we can solve for FDC. To solve for FDC, we're going to do 3.61 cosine of 30. Bring this to the other side of the equation. Divided by the sine of 36.9. And we get FDC is equal to minus 5.2 kilonewtons. So this is equal to 5.2 kilonewtons in compression. So there you have it. These are all of the forces of all of the different members. And this is what you're looking for when you're solving a problem of method of joints.